At this time in our note pack, we've talked a great deal about writing electron configurations, the rules for following called Pauli exclusion, the Aufbau principle, and Hund's rule. Talked a little bit about the electromagnetic spectrum, and that spectrum shows the visible wavelength here, the Roy G. Biv, if you will, in terms of excited electrons. What we'd like to do now is just take a peek at processing a section review. So I'm on page 6 of my note pack. Section review allows me to just solidify some learning that has gone on so far. Read with me. How many electrons are in the highest occupied energy level of these atoms? The highest occupied energy level. The first element is barium. Barium has 56 electrons. What would be the highest energy level we would write for? We could count through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and here we are landing at barium, 6s squared. I just went through and rattled off. Don't be impressed. I could follow the yellow brick road and write out an electron configuration until I've written for 56 electrons. But I can now kind of start to predict the last thing I'm going to write would be a 6s squared electron configuration. The sixth energy level will have 2 electrons. 2 valence electrons from the group 2a. Period 6 tells me that it's the 6th energy level. Barium would have 6 as its principal energy level. That's the highest occupied. The period number told me so. It's that easy. How many electrons are in the highest occupied energy level? Well, I can see in the 6th energy level, we would have 2 electrons left to place. They would go in the s orbital. The highest electron arrangement would place 2 electrons in the 2nd energy level, or in the 6th energy level, 2 in the s sublevel. Now let me clarify. Perhaps some of you have printed off a test-taking tool page that was on the Moodle site. It looks a lot like this one here, and it might as well take a minute and kind of get oriented. On the far left, we have the S block. On the far right, we call that the P block. In the middle is the D block, and down below is the F block. This comes up again later on. I'm just kind of introducing, kind of seeding a future lesson, that the arrangement of electrons is very predictable by where the atom lives on the periodic table. Notice what I just did to rattle off barium. I followed the periodic table as if it were a sentence reading left to right in a book. 1s2 gets me from hydrogen to helium. I hit the end of the row, so I come back. 2s2, lithium beryllium. 2p6 carries me all the way through neon. Boron is 2p1. Carbon would end with 2p2. Nitrogen would end with 2p3. Oxygen 2p4, and so forth. I hit the end of the row. I come back. 3rd energy level, period 3. Sodium, magnesium. Sodium would be 3s1. Magnesium would end with 3s2. The next tall column I hit is aluminum. It's still period 3. 3p1 would be the last thing I write for aluminum. 3p2, the last thing I would write for silicon. 3p3 for phosphorus. p4 for sulfur. 3p5 for chlorine, and so forth. 4s squared takes me through calcium. Notice here I go back after the 4s. I'm actually filling the 3rd energy level, D sublevel. 3d10 takes me to zinc. Go back to the period number. 4p6 gets me to krypton. 5s squared, 4d10, 5p6. Went through that 5th period. The D block always one behind the period number. This row is what period it's in. This row, this little number tells me the energy level. By the time I've gone through to find barium, I'm in the 6th energy level. And the last thing I wrote was S squared, 6s2. There are 2 electrons occupying the highest energy level. The last thing we would write would be 6s squared. What about for sodium? Use this test-taking tool page. Here's sodium. It lives in period 3 in the first column of the S block. 3s1 would be the last thing we write for sodium. Its configuration would look like 1s2, 2s2, 2p6, 3s1. That's 11 electrons for the element sodium. The last thing we would write, 3s1. There's 1 electron occupying the highest energy level. The period number tells me what energy level I'm in. The group number tells me valence electrons. Valence electrons means how many electrons are in the outermost energy level. Barium, there were 6 principal energy levels, and in the last one of those, there were 2 electrons occupying the S sublevel. Sodium has 3 energy levels with 1 electron occupying the outermost electron orbital. What about aluminum? Aluminum, its configuration, 1s2, 2s2, 2p6, 3s2, 3p1. I'm going to write that. I'll have room right here. 1s2, 2s2, 2p6, 3s2, 3p1. The highest occupied energy level is the 3rd energy level. In the 3rd energy level, there are 2 electrons in the S sublevel, 1 more in the P sublevel, for a total of 3 electrons in the highest occupied energy level. 2 of them placed in the S sublevel, 1 more in the P sublevel, equaling 3 electrons in the outermost energy level. Notice aluminum in group 3A, 3 valence electrons, 2 of them in the S sublevel, 1 more in the P. Let's write for oxygen. Oxygen's configuration, 1s2, 2s2, 2p4. 2p4 is the last thing we write for oxygen. Let me write that somewhere. How about down here? 1s2, 2s2, 2p4. The last thing we write for oxygen is in the 2nd energy level. There are 6 electrons in the highest occupied energy level. Notice where oxygen lives in group 6A. Period 2, in the 2nd energy level, there are 6 valence electrons. 2 of them reside in the S sublevel, 4 more of those reside in the P sublevel. The entire 2nd energy level contains 6 electrons. Let's continue. Pause if you need to. Digest what I've said. Give yourself a self-check before you go on. Important in video lessons, you pause when you need to and start up when ready. We're going to be writing electron configurations and orbital diagrams for the elements identified by the following atomic numbers. Well, in number 15, that identity is phosphorus. He's number 15 on the periodic table. So we're writing for the element phosphorus. Use your test-taking tool and get an idea of the last thing we'll write for phosphorus. Phosphorus is right here in the 3rd period, 3 over in the P block. The last thing we'll write would be 3p6. 2p3. And I bet that gets us to 15 electrons. Read the periodic table as you would a book, left to right, just as you would a sentence. 1s2, 2s2, 2p6, 3s2, 3p3. Or this way, 1s2, 2s2, 2p6, 3s2, 3p3 gets me to the 15 electrons of phosphorus. Let's write the orbital diagrams for just the valence electrons. Those electrons in the outermost energy level, the third energy level, the highest quantum number 3. There are 2 electrons in the s sublevel, 3 more in the p sublevel, each one placed into an orbital first before assigning a partner, all spinning the same way. There are 5 valence electrons. Phosphorus lives in group 5a, period 3. 5 electrons in the outermost energy level. The outermost energy level is quantum number 3, third energy level. 2 in the s, 3 more in the p. Let's find number 12. Number 12 is magnesium. Number 12 is magnesium. Use your test-taking tool and decide what's the last thing we're going to write for magnesium. Magnesium is period 3, 2 over in the S block. The last thing we'll write is 3s2. That will get us to 12 electrons. 1s2, 2s2, 2p6, 3s2. 2 and 2 is 4, 6 is 10, 2 more gets me to 12, our target number. The outermost energy level is quantum number 3. There are 2 electrons in the s sublevel. Magnesium lives in period 3, group 2a. 2 valence electrons that reside in the third energy level. Let's find number 9. 9 is the element fluorine. Hang on, let me get the screen back, sorry. Be patient, just a moment. Keep watching. Alright, I think I have my screen back. I'm sorry, we were working on number 9. Number 9 is fluorine. Group 2A, period 2A. Period 2, group 7A. Now I'm flustered. Period 2, group 7A. Now on our test-taking tool, period 2, the first 2 of electrons in the S subblock, 5 more in the P for a total of 7. So writing for fluorine, number 9, 1s2, 2s2, 2p5 gives us 9 total electrons. 2 in the S sublevel, 5 more in the P sublevel, and again, it absolutely doesn't matter which one you leave without a partner. They're all of equal energy. So here is the highest occupied energy level 2. There's a total of 7 electrons in the outermost energy level. 2 of those reside in the S sublevel, 5 more reside in the P sublevel, for a total of 7 in the highest occupied level. One more to write, number 19. 19 is the element potassium. Potassium resides in the 4th energy level, period 4, in the first column. The last thing we'll write is 4s1, and when we write that, we'll have written for 19 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Gets me to the 19 electrons that we needed for potassium. In the fourth energy level, we have 1 electron in the S sublevel. Number 3, what element given by the symbol corresponds to each of these configurations? What we're looking at is an address of a number of electrons, and we're trying to identify the element. Some of these appear to be ground state configurations, and when I say ground state, it appears to be following all the rules in their electron arrangement. 1s2, 2s2, 2p6, 3s2, 3p6. This indeed follows the correct arrangement. 1s2, 2s2, 2p6, 3s2, 3p6. It's exactly what we wrote. So it's a ground state, the normal lowest energy level arrangement. I think the easiest thing to do is to count superscripts. 2 plus 2 is 4. 6 gets me to 10. 8 more. This is element number 18. 18 is argon. On our test-taking tool page, argon lives in the third energy level. The last thing we wrote was 3p6. 3p6 corresponds to argon. Now I'm noticing B and C are excited. In other words, they've promoted some of their electrons to energy levels they would not normally reside in. The excited state happens when electrons absorb energy, either by a source of electricity getting zapped with some power, or by heating them in a flame. Somehow the electrons have absorbed extra energy and have bounced out to higher energy levels. That's not normal. It only happens for an instant. But the excited state, I can pick those out because they're written in a way that's not following the 3 guiding principles, the Aufbau, the Hund, and the Pauli exclusion. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. If I look at here, I have 5s1, 4d7. I'm just seeing that the arrangement is not following my electron pyramid by the diagonal lines. It's still easy enough to find what element in an excited arrangement. Count up the superscripts, and that's the atomic number. 2 and 2 is 4. 6 more gets me to 10, 12, 18, 28, 29, 30, 36, 37, and 7 make 44. Number 44, Ru, ruthenium. The number of electrons we counted, I'll count again just to be sure. Here's 10, 18, 28, 29, 30, 36, 37, 38, 39, 40, 41, 42, 43, one more, 44, ruthenium. 2 and 2 is 4 and 6 make 10. Here's 18, 28, 29, 30, 36, 46, and 14. 2 more, 6 more, and 3 more. Number 71. 71, down here, Lu, lutetium, Lu, lutetium, Lu. So that's all we're doing in that particular area, is just noticing the number of electrons represented by the superscripts gives me the identity of the element. Even if they're not necessarily following the correct rules, they might be in an excited state or the ground state, but the identity of the atom simply comes from summing the superscripts to get the atomic number. You should pause the video here and check for your understanding.